There should be another hydrogen here too. I think that was a CH2 in the example. Is that right?
Wait, what is that called?
We did a hydride shift. Remember when we were doing substitution and elimination? And we said that sometimes you can do a hydride shift and go from a carbocation that's less stable to one that's more stable. And let me rewind this. So this is the beauty of doing. So the plus charge was on this carbon, is that right? And then when we shifted the hydrogen over to that carbon, and so it's the hydrogen and the electrons, right? We ended up with the plus charge being, I'm cheating, but we ended up with the plus charge being here, and then that other hydrogen being here.
Where's the hydrogen that you grabbed from the first part?
Say that again.
Like, where's the hydrogen that you grabbed when you did that first part where you highlighted that double bond and broke it?
Where's this hydrogen right here? Is that what you're asking?
Yeah.
Oh, it's here. My bad. So it's adding to this carbon right here.
Oh, okay.
Thank you for saying something about that. My bad, my fault. Yeah. All right. So now would this give me, if I added Br minus to it, would that give me the product, the same product?
Yes.
It would. This would come and attack here, and it would give me the same product that we had here, C. All right. Let's. Any questions about that before we do another one?
Can you go back down to the bottom? Okay. Where's the because up there it says you have the CH2 and then it goes down to CH3.
Right here.
Yeah.
So remember in this reaction, when that double bond attacks HBr, the H has to add first before we make the carbocation.
Oh, okay.
Right. So the H is added to that end, to the terminal carbon.
Okay.
Any other questions?
No.
All right. Let's do this 1649 or 48, my bad. It says explain with reference to the mechanism why the addition of one equivalent of HCl to diene A only forms two products of electrophilic addition, even though four constitutional isomers are possible. All right, so let's think about that. Let's look at the products. And I have a chlorine that ends up on this carbon here, and then a chlorine that ends up on this carbon. So how do we explain that? Which double bond do you want to start with?
Would it be because one of them is not an active reaction site?
Say that again.
Would it be because one of them is not like an active reaction site? The reason why it forms two instead of two.
Let's see. Let me just get a blank spot so we can work that. There we go. That'll work. So this is the starting material plus HCl. Let's start with this double bond right here, right? If we attack the HCl with that, right? What does the intermediate look like? Let's just get to both intermediates and then we can probably figure out. So you can have plus charge. Right, so that's one intermediate. And then what would the intermediate look like if I use this alkene?
Dr. Russell, why is the plus charge at that bottom carbon instead of the top one that you had it at initially?
Say that again. Why did I move it?
Yes.
Okay, that's a good question. So if you look, if I put it here, right, it's still allylic because it's adjacent to this alkene, but can we stabilize it by resonance though?
Okay, no.
We cannot, because remember those bonds in the benzene ring don't react, right?
Okay.
So that's why I moved it here. So now it's allylic on this site, and you can stabilize it through resonance with this alkene right here.
Okay.
Yeah, good question. Can you see my phone? It's in the kitchen. Okay. Sorry about that. That was my son. All right. And then is this the other intermediate? We do this as 1 and 2. If we use double alkene number 2.
When I found I used the intermediate number 2 to find both of the products.
Say that again.
I use intermediate number 2 to find both of the products.
Let's see.
One is direct, and the other one has like a has resonance. The double bond moves to make it form the second product.
Let's see. So you're saying, let me find where we were. You said if we use double bond number 2, we're going to get both products.
Mm-hmm.
Yeah. All right. So yeah, you're right. If chlorine can come in here, or it can come in here and shift that over, and that'll give us this. Plus that, right? And those are the two products that are predicted. Is that right?
Yes, that's right.
And it says we only get those 2. It says we only get those 2 and not the 2 other products where this alkene here is used. Says even though 4 constitutional isomers are product or possible, we only get 2 products. So why do you think that the other alkene wouldn't react? What would be your guess to that?
Benzene? I don't know.
Yeah, why do you think alkene 1 doesn't react?
Dr. Russell, I might have to leave a little early because I have a testimony. So,
Okay, that's fine. It'll be recorded, so it's no problem.
okay, thank you.
Mm-hmm. Any guesses or any ideas as to why alkene 1 doesn't react? Well, I have a suggestion for why alkene 1 doesn't react. I think that because it's conjugated with the ring, I think that makes it less reactive than alkene 2. And so for that reason, alkene 2 is, if it's more reactive, that's where your products are going to come from. It's always difficult when you add in a benzene ring because that just changes the reactivity so much. And I think that because that alkene is conjugated with that ring, that it won't react because you're breaking up, like, I think you'd lose something like 5 kilojoules per mole of energy for breaking up conjugation or something like that. So that's my suggestion.
So you said it's because it's connected to the ring?
Mm-hmm. So it's in conjugation with this ring. You see how all these other double bonds are conjugated with it?
Yeah.
Yeah. So I think that makes it less reactive. Let me change the color right quick. So I'm just going to say it's less reactive to the ring. All right. So are there any questions about this? I know it's a lot. And I know it's even more because you're sitting at home watching it on the screen and not sitting in a classroom. So
I have a question, Doctor.
go ahead.
Okay, so the 2 products shown in the problem, they all came from the second.
Yes, from the use of alkene 2.
Okay.
Did you try to react it and it just didn't
Say
work?
that again.
You tried to react it with the first alkene and it just didn't work because of the ring, or
Yeah, I think the alkene 1 is less reactive because it's in conjugation with the ring. I mean, we could look at the products and see what we get from that. And then we can. That's one of my products. And then the other one would be that. So you really
possible, but it don't react as much.
Yeah, I don't think it's everything is possible, but I don't think that you'll get those 2 products because if you notice, you see how like right here, that conjugation between that alkene and the ring is gone now, and the same with this product, right? So you feel me? So you really lose a lot of energy by breaking that conjugation up because the benzene ring, if it's conjugated with an alkene outside of it, that alkene basically is an extension of that pi system, right? Because we did say that up front, right? That if it's conjugated, it's one big system.
Yeah.